My friend introduced me to a really interesting problem about probability a few days ago, and I just wanted to share it with you guys. So here's the premise. There's this baby on a couch, and it has an 80% chance of staying on the couch and a 20% chance of falling off the couch and face planting on the ground. When the baby is off of the couch, it has a 50% chance of staying exactly where it is, a 30% chance of crawling backward, and a 20% chance of crawling forward. If the baby is allowed to make infinite moves, what is the chance of the baby staying on the couch? And no, it's not zero. Pause the video and think about it for a second. I originally had no idea of how to approach this problem, so it's okay if you don't either. Let's first set this system up as an infinite line of nodes. The key concept is that instead of physically imagining the baby moving back and forth from these nodes, you have to treat each node as if the essence of the baby is flowing through it at a rate determined by the probability of the possible moves. It's kind of like you have a line of infinite buckets, each pouring into each other at a predetermined rate. Therefore, you can define the probability of the baby being at any node by the rate of exchange of baby with the two nodes adjacent to it. Let pi of n be the amount of baby sitting at node n once the system settles. At steady state, each node's level holds constant, so pi of n is just the sum of three inflows: the baby that stays, the baby crawling in from behind, and the baby crawling back from ahead. Notice that the coefficients are from the probabilities of each action laid out at the start of the problem. After some rearranging, we get that 5 pi of n is equal to 2 pi of n minus 1 plus 3 pi of n plus 1. Now, if you were being very observant, you would notice that this kind of looks like a Fibonacci series. It turns out that anything in the form of a Fibonacci series can be modeled by an exponential function. I could go into why this works, but that would be a topic for a whole nother video. So, any term pi of n is equal to a times r to the n. After plugging this into our equation and some more work, we get 3r squared minus 5r plus 2 equals 0. Solving for r, we can see that r equals 2/3 or 1. We will test out r equals 2/3 first and justify later why r equals 1 is not a solution. Okay, now let's try solving for the probability of the baby being on the couch. Since the couch is pi of 0, a times r to the 0 is just equal to a. Okay, minor issue. What the hell is a? But we have a saving grace. We know that the sum of the probability densities of the baby at each node must be equal to 1. Therefore, this infinite sum is just equal to 1. This is just an infinite geometric series. So, first term being a over 1 minus 2/3 equals 1, and therefore a equals 1/3. We see why r equals 1 doesn't work in this problem now, since if r equaled 1, we would get an infinite sum of a's, which obviously can't equal 1. There we have it. The probability of the baby being on the couch is equal to 1/3.